So good afternoon and welcome everyone. And I am Ion Stoica. I am a faculty at UC Berkeley, and I am also a co-founder and executive chairman at Databricks. And I am today together with Rahul Bhatia from Amazon, AWS. We are going to talk about two things. First, we are going to give you a short update on Apache Spark with a focus on Apache 2.0, which was released earlier this year. And then we are going to talk about some best practices about how to run Apache Spark in AWS. So let me start with a short history. Apache started as a project, as a research project back in 2009. When we started Apache, it's actually we were also using Amazon. We were some of the early users of AWS. And not surprisingly, a lot of development and testing happened on EC2 from day one. So you could say that Apache Spark was kind of built for the cloud from early on. It becomes open source in 2010, and then it becomes a top Apache project in 2013. And today, it's the most active big data project. And it's growing very fast, and actually, by some metrics, or most of the metrics, the growth is accelerating. So it is nowhere like slowing down. So here are some numbers. The number of contributors has increased by almost 50% since last year. The number of summit attendees, we ran 3 Spark summits, one on the East Coast, on the West Coast, and one in Europe. This year was over 5,000 people. And probably the most impressive figure is the number of meetup members across the world. It, from last year, increased by over 4 times. And actually, that number, if you look now, probably is over 280,000. It's growing very fast every day. Also, as you know, and many of you here, Apache Spark now has a tremendous moment in industry. It's running in clouds, of course, starting with Amazon EMR. And many companies provide it, both as a service. Databricks provide an end-to-end enterprise-grade solution on top of Spark. Then every big data vendor today, it actually includes Apache Spark in their distribution. The one thing, I think that is pretty well known by this time, but I just want to make sure, is that Apache Spark was released. It was built from the ground up to take advantage of the increasing memory you have on the servers. So people understood very from early on that Apache is fast, and it's fast because it's using memory for storage and computation. However, Apache is not fast when you have and you can push the data in memory. It's also fast when the data is on the disk or on SSD. And this is from actually 2014. Apache won the greatest sort benchmark, the best numbers. And to give you a sense, the past year, the record was held by a cluster from Yahoo, Hadoop cluster, and this was sorting like this 1 terabyte data using over 2,000 servers, and it took 72 minutes. In 2014, Spark on Amazon on the EC2 took 3 times less time, and on 1/10 of the machines, right, of the number of machines. And in this case, the bottleneck was a communication network. It's actually, we could push the network to 10 gigabits per second per host. That's the limitation there. So the takeaway here is that if you use Spark, it's not only good for when your data fits in memory, it's also very good at any scales and when the data is stored out of memory. So next, I would like to talk about Apache Spark 2.0. So Apache Spark 2.0, it was released earlier this year, and it's actually incorporates the biggest changes in Spark since we released it in 2009. And the features in 2.0 can be grouped in 3 categories. The first one has to deal with the APIs. And in Apache 2.0, first of all, we have a much more mature SQL. So actually, we are pretty much follow the SQL 2003 standard. And the other major thing is that we are raising the level of abstractions from RDDs to DataFrames. So as all of you know, RDDs was a main data abstraction in Spark. RDD stands for Resilient Distributed Dataset, and is basically a collection of tuples, which is distributed across the machines, and each tuple has a key and a value. The value has no semantics for Spark, it's just a blob, okay? And DataFrame, in turn, it's actually, think about it as a table, right? So it's not only a key and a value, it's basically a bunch of columns, and each column has a data type, okay? So you have a lot of richer semantics. The operators on data frames are mostly relational operators. Think about SQL kind of operators, with a heavy emphasis on statistical analysis, like quantile, standard deviation, skew of the distribution you can compute just with a simple command. The data frames was popularized by R and Python with the pandas communities, and they are today, and they've been used largely by data scientists, okay? So and what data frames, again, I tell you, it's a table, has more semantics, columns, types for each columns, and so forth. But what does this buy you? So it buys you 2 things. First, it makes it much easier to write programs, right? It's a higher level API. And to demonstrate this point, here is an example. This is using RDDs. It's a snippet of code. And I'm going to ask you, anyone knows what this code is doing? Okay, don't feel bad. It's even, Spark people, it's heavy-duty programmers may have difficulty getting what this is doing. And what it actually is doing, I can show you next, and this is the next line of code, is the same functionality implemented using data frames. And here it is. Now I hope that almost everyone can understand what this is doing, right? It's averaging the age by department in an organization, okay? So again, data frames has more semantics, and because of that, it makes it much easier to write programs, okay? This is the first advantage. The second advantage of data frames is because you can use these semantics to better optimize the algorithms. In particular, right now, if you now, let me just take a step back. You know that on top of Spark is an ecosystem. You have Spark Core, and you have a bunch of libraries on top of it to support different workloads. One is to support SQL workloads, and is Spark SQL. Spark SQL has an optimizer called Catalyst. And now with data frames, which again are tables, like in SQLs, and I told you that data frames operators are mostly relational operators. What we can do is that we have all the data frames operators using the same logical plan like SQL. So you unify the data frames and SQL, and they share the same query optimizer and the same execution engine. Data frames are also tightly integrated with the rest of Spark. Machine learning libraries takes data frames as both inputs and the outputs. And you can still, if you really want to use RDDs, it's very easy to go between RDDs and data frames. Okay? So why do you care about this? You care about this because every optimization, you can do this in logical plan or the execution, is going to be inherited and is going to be available to everything and all the programs you write on top of Spark using data frames now. Okay? And to make this point, here is a benchmark. These two lines represent, it's an aggregation. You aggregate a bunch of numbers. This is not exactly important what numbers are those. And here it's the implementation of these aggregations for Python and Scala using RDDs. So this is before data frames. Okay? And the time it's on the x-axis. So what you can see, you have a difference in times, although it's logically the same operation. The reason is because you have different implementations, and Python, it's in this case, it's a little bit less efficient. It shouldn't be a surprise because, as you know, Spark was developed in Scala, so it's Scala native, right? Now, here what happens after using data frames. So there are two things to notice here. First, whether you do aggregation using data frames in Scala, Python, R, or SQL, it takes the same amount of time. Why? It's again because underneath now, all of them, they share the same logical plan and the execution engine. Okay? The other thing is that it's better, right? And this is because we made a bunch of optimizations which are enabled by the data frames. So I'm going to talk a little bit about that next. So the second set of features have to deal with improving the performance. And internally, the project which was doing this, that we pushed at Databricks, was called Tungsten. And at the end, we got improvements in the speed between 5 and 20x. So what is Tungsten doing? On one hand, it's doing these typical database optimizations. It's, again, over data frames and SQL, like join ordering, push down predicates, and things like that. It's improving on the data representation. You can use compact binary representation. I'll talk a little bit more about that next. And it's also doing more sophisticated optimization, like whole score generations. Remove expensive iterator calls, fuse across multiple operators. So at a high level, what this means is that if you have multiple operators in a queries, like filtering or things like that, or aggregation, instead of every operator going through the entire table record by record, right, scanning the entire table, you fuse the operators, and you have multiple operators going, through a record, right? Okay? So instead of operator 1 going through the tables and then operator 2 going through the table, you have operating 1 and operating 2 going through a record and then the next record. So you go through the table only once. And this has significant benefits. Like, for instance, of course, you have fewer scans, and also it has much better cache locality. Okay? So this is, the other thing what data frames enables, it enables us to be much smarter and more efficient about managing the memory. So stepping back with RDDs, typically when you load the RDDs in memory, you deserialize them, okay? And you create Java objects. And I'll give you an example next. But you are going to end with a huge number of Java objects, which will take a lot of RAM, memory. Actually, the memory overhead is 4 to 8 times more than the serialized format. So if you have 1 gigabyte on disk, You load it in memory, you deserialize it, you are going to end up with 4 to 8 gigabytes. And if you have a lot of objects, then you have the garbage collection problem, right? Because Spark, it's using JVM, right? And it has also a little memory locality and cache locality because you have to jump over to get the data across all these pointers. With DataFrames, because we have more semantics about syntax, we know the syntax of the data, we know their format, we can actually keep the binary format in memory. So you can keep entire table in memory. It's one big object. So much, much fewer objects, so we don't have the GC problem, garbage collection problem. Much lower memory overhead, almost no memory overhead, and much better cache locality. So here is to drive home the point. This is how it's, again, there, if you like RDD, it's a key value. And when you load it, this is kind of something what you get in memory. This is a hash map. And you see you have a key value. This is your entry. And this is what Java is doing, is keeping a pointer for the key, a pointer for the value, and a pointer to the next entry. So you have 3 pointers there. So actually, if your key and values are integer or something like that, you have more pointers than actually useful data. And when you scan or whatever, you need to jump to get all these value, keys and values, through the memory. And here, what you can do is DataFrames and how we can manage the memory. So with DataFrames, we just maintain all the table, right, all the data frame in one big memory blob, okay? And because we know the value, what each of them represent and what is their format, we know, so if we need to read, for instance, the 10th row from the data frames, we know exactly how to get there, right? It will be an offset from the beginning of this page, memory page, which contains the data frame, okay? So how good and are these optimizations? Here it's TPC-DS. As you know, it's a standard benchmark for big data, for SQL workloads. And with yellow, it's the time for Spark 1.6. It was the last version before 2.0. And with blue, it's 2.0. So you can see if this is all these queries, the performance, it's increasing by a factor, or the latency is decreasing by a factor of 10 in some cases. Okay? So it's a pretty massive performance improvement. The last category of features in 2.0, it deals with structured streaming. So they are related with streaming. In a nutshell, structured streaming is also taking these data frames and provide you a data frame-based streaming API. So it's very similar when you write a streaming application or you write a batch application in Spark today with 2.0, the code will look pretty much the same. What is the intuition behind that? Well, because if you think about the main difference at the high level, okay, there are more differences, but at the high level, the difference between something like a batch application and a streaming application is that in the case of the streaming application, we have infinite tables. Because the new logs are new rows which are continuously added to the existing tables. That's the difference. So once you can export that abstractions, now the operators are very similar. And this allows you to do a lot of cool things. Also, they are enabled because all of them, again, they share the same logical plan and execution plan. So let's see what you can do. First, let me start with what typically you do with the streaming systems. So here, how a streaming pipeline looks like. you get something in Kafka or Kinesis, you do some ETL, and then you store your logs in the database. If you have an IoT application, this is kind of what you do. Or you do some reporting, or you do some dashboards. So you look at the data. Or you can be consumed by some applications, maybe to trigger when something is greater than a threshold. But what you can do in Spark, which is difficult to do otherwise, which is unique in Spark, is because all these workloads are integrated. And again, they use the same execution engine, the same data formats. You can do, for instance, ad hoc queries on the stream data. So think about the following scenario. You get the data, you get an alert on your data. You monitor a set of logs from your clusters or IoT devices. Then on that alert, you can immediately go and do ad hoc queries to figure out what's happening, right? On the data as it's streamed. Or, you hear more and more about this, you can do machine learning, online machine learning. The data comes in, as soon as it's coming in, you feed it to the machine learning algorithms. So you can continuously update the model. So this allows you to make decisions much faster or much fresher data. Okay, so this is pretty much about 2.0. And now I'm going to hand to Rahul to tell you some exciting things about how to use Apache Spark on EC2.
Thank you, Ian. Thank you very much. So that was a great talk. I mean, we learned about, in terms of structured streaming, we learned about DataFrames, we learned about Tungsten. But if you think about it, this is about Spark, and how do you translate that on AWS as a platform? To think about that, let's look at what are the options you have. In terms of the first option, the first choice what you get, anytime you're thinking about, doesn't matter what are you using to run Spark on AWS, the first option comes to your head is which type of instance I'm using, right? Am I using a memory optimized? Am I using a storage optimized, compute optimized, or even a general purpose instances? And if you think of it, each of them lends to a specific class of workload which you mentioned. If you read deeper into what Ian talked about, for instance, like how Tungsten has off-heap storage, which is much more customized. So now you could leverage an instance like X1, which provides you 128 cores with 2 terabytes of RAM. And you can think of that as a many workers running, sharing a same 2 terabyte of memory. The implications of that could be, for example, let's say you're running a very heavy sort workload, which is doing a lot of data transfer across nodes. Now, since all of the data could be localized on the same machine, it could help you in those kind of situations. But again, the workload has to be the environment where there is implications in terms of how you store the memory, in terms of how the memory gets transferred, or how you can optimize it. And as you said, the Tungsten provides you the off-heap memory where you don't have to worry about the JVMs. In a traditional model, to leverage this kind of system, you will have to run multiple Spark workers on the same machine, each of which is using a JVM. And every time a JVM is trying to talk to other JVM, you're doing some serialization in between there for them to communicate with each other. But this way, you could reduce that because the workers are using a shared memory model, if you will. And not only that, if a JVM crashes, the off-heap memory still lives on, which means when the new JVM creates, the new worker comes, it can just start using the off-heap storage rather than having to deserialize the whole thing again. That's one of the examples, for instance, where you can run a memory-optimized workload much more efficiently on Spark using the X1 platform. The same will apply for R4s announced yesterday, for instance. Or if you look at it, in cases, it's a common misconception that with Spark, everything has to fit in the memory. Ian talked about the sorting which we did using on AWS, a terabyte sort benchmark. And if you really read the benchmark outputs of it, what you will realize is Spark, in this case, was optimized by the community in terms of using the local storage or using local SSDs, which was there on i2s to run the benchmark. Or for instance, if you think about i3s, which was announced yesterday, they can give you up to a 3.3 million IOPS or 16 gigabyte per second of throughput to the NVMe-based local disks. And in that case, the boundaries between how you use a memory or how you store your data on SSDs actually becomes very seamless. And Spark gives you the ability to store the data set in there. For example, sometimes you may have, when you create an object from streaming, you may have put a parameter which is called memory and disk, for example, if you ever noticed, right? But what it's telling you is Spark is like trying to share a copy in memory and store a copy in disk itself. Not only that, there are optimizations in the sense of, like, for example, when you run SQL queries, how Parquet could help in terms of columnar storage, could help you run those queries very effectively, even when data is stored on the disks, rather than having been cached in memory. This is primarily if you're running some things which are very data-heavy workloads. These are a great instance for you to run that kind of data-heavy workload because you have a lot of data and you can store the data in outside heap back in the local storage itself. But if you look a bit further, now as you move from a query workload, as you move from a data processing workload into a algorithm-based workload, like a numerical computation, this is where GPUs start giving you the power, giving you the benefit of it. The P2 instances, for example, gives you 16 NVIDIA K80 GPUs. And how do you utilize that? To run that on Amazon, you have Amazon Linux Army, which is available as a standard. All of the libraries installed, so you can start running your machine learning workloads. Databricks in their blog announced that they're going to soon add support for P2s with Spark. But if you really think about it, when you run a workload, when you want to utilize a GPU-based computation in Spark, something like TensorFrames, for example, what happens in that case is you have a Spark memory model, and then it gets translated from Spark to a Java, then Java baked to another C++ TensorFrame or TensorFlow-based object. That serialization, deserialization, that communication takes a lot of time. In fact, if you want to learn more about it, there's an awesome talk by Tim Hunter on how he talks about how TensorFrames works underneath the scenes. And with TensorFrames, what is happening in terms of GPU, what is really happening is that you have a Tungsten binary object, and the object does not get serialized, deserialized in between different layers of communication, from CPU, from back to Spark DataFrames, from back to a TensorFrame object in there. And this gives you benefit in terms of speeding, running workloads like kernel density scoring, which is basically a way to estimate the probability density function of random variables. And it tells you that when you're running that using a TensorFrames alone on a compute instances versus on GPUs itself. And you can see the 60x throughput difference in terms of how fast it can run TensorFrames using GPU, where we have removed the communication channel, communication barriers between different layers of that processing. So these are a few examples where you can see how you can use memory optimize, how you can choose storage optimize, or how you can run a GPU instances with Spark on AWS, and how you can leverage those for running your workload. Now, the one thing we all have been stressing about in this talk was that Spark is being used for computing. You have your data stored somewhere else, be it S3, be it Redshift, be it Aurora, DynamoDB, and you're reading that data back from one of these sources into Spark. You're computing your object, you're computing your processing, and writing it back to somewhere else. But Spark is not a storage engine. It can store data for computation, what it needs, but it's not really a computation engine, a storage engine. So what that means is that it gives you advantage to use things like Spot instances. Because it's not a computation, it's not a storage engine. If your compute is lost, it has the ability to recreate the compute from the lineage it stores, from the information it stores, from the redundant data copies it stores, and get you back to the same stage. And using Spot, you can run your workload much more cheaply, much more efficiently on AWS. Sometimes you can have savings as much as 10x, for example, where you can leverage a Spot to run most of your Spark workloads on AWS, since your data is living outside of the Spot. So even if the Spot goes away, the Spark will make that transparent for you. Most of the frameworks will make that transparent for you. And when you run it, it's a good idea, make sure that you're not running your driver on Spark, because if the driver goes, then you're in trouble. And of course, have a mix of Spot plus on-demand or RIs or whatever you have, so you could, even if the Spot gets taken away, you still could complete your work. If you run everything on Spot, then you may end up losing some work. But few things, again, just in general, which is that first is enhanced networking. Spark needs a lot in terms of communicating between each other. And if you're running a workload which needs a lot of data transfer, for instance, between two nodes, for example, query processing, sorting workload, for example, where a lot of data needs to get transferred between two nodes itself. And this is where you could use things like enhanced networking, which gives you flat, very high packet per second, or elastic network adapter, where in case of benchmarks or in case of running workloads like sorting, where a lot of data is being transferred between nodes running in a cluster, you could leverage 20 Gbps, which is there with M4, 10x, 16x large, the largest of the instances like P2s, X1s, and all of them can give you up to 20 Gbps of connectivity when you place them within a placement group. In fact, the sorting benchmark was run on the instances being running in a placement group, because a placement group is where it provides you that kind of bandwidth. All the 10x cells, or all the nodes which says that they have 10 Gbps network or 20 Gbps network, that's where you can leverage the placement group to keep them, get the leverage of the bandwidth, in case your workload is where a lot of data is getting transferred between two nodes. Now, these are some of the choices you have today in terms of running the workload, but the question still remains. So we learned a lot about what Spark is, what are the benefits of Spark 2.0. We learned about some of the choices available to you in AWS in terms of running your workload. But which instance you choose? How do you figure out what to run, where to run it? And for that, I would again invite Ian to talk about how you can choose the right instance, how you can choose the right size on AWS. Thank you.
Thank you, Rahul.
Yeah.
Yeah, so like Rahul mentioned early on, today, Amazon is doing a fantastic job giving you choices, right? And the last time when I looked, there are over 100 type of instances you can choose from. And every day they add new ones, right? So then it's a very natural question. On one hand, you have your application. On the other hand, you have all these other choices. So the question is basically how many instances you need and what type of instances you should use for your applications. So in the rest of the talk, I'm going to try to address these questions. But the first question, before even going in which instances you are going to use, which type of instances, how many, the first question is, does it matter? Right? If it doesn't matter, why do you care, right? You pick whatever. Well, it turns out that it matters, like you'd expect. And here is just a micro benchmark. It's a matrix multiplication. And you have 5 configurations. All the configurations, they have the same kind of memory and cost the same resources, the same cost. But they differ by how many instances you have. And you see in this plot, on the y-axis, you have the time, how long it takes to multiply these matrices, and how much for each configuration, how much it did take for each configuration to multiply these matrices. So maybe not surprising here, if you can fit everything on one machine, you get the best results, the dark blue line, right? So, okay, so maybe this will imply that maybe it's a simple rule. I just try to consolidate as much as I can on the fewer instances as possible. It turns out that that's not always the case. For the different workloads, and this is QR factorization, it's a linear algebra, another linear algebra, micro benchmarks. If you look at the same configurations, you get very different results. In this case, the one machine configuration is the worst. And having more machines in this case is the best. Okay? Again, cost you the same amount of money. And intuitively here, the reason for the matrix multiplication is much better if you don't want to do it on a machine is because the communication is a bottleneck in that case. In the case of QR factorization, you can parallelize it much more effectively, and now you can do all this. The bottleneck is how much and how fast you can do on each machine. And if you have more machines, the aggregate memory bus, if you do if you have 2 machines, you have twice as as almost twice as much as capacity to the memory, of the bus to the memory, you are going to do better if you have more machines, right? Because the aggregate memory bus bandwidth is higher if you have more machines. Okay, so now what you are going to do about it? So we developed at Berkeley a tool which is called Eamest, and it's available. It's an early release. Please go ahead and you can check it out. And the goal of these tools is that giving a job to tell you how many instances and how many of these instances you should use for this to run your job, right? What type of instances and how many instances. And the way it's doing it is that going to run your job of a smaller data set, much smaller data set, right? So you have to process 1 petabyte, it's going to run on a few megabytes or a few tens of megabytes. And it's going to somehow triangulate and it's going to figure out what type of instances you should use and how many of them, okay? And you can use it in 2 ways. On one hand, you can say, I want to spend so much money, so tell me which instances I should use so that I run the job the fastest. Or I want to run this job, like think about the ETL job, like by sometimes you need to process the data, say, from the previous hour or the previous day, so you have a deadline. What is the cheapest way I can run this job to meet my deadlines? Okay, these are the 2 ways. This is an example showing again, it's showing how that in this case you have the same type of instance, the same instance type, R3X large, and on the x-axis we vary the number of machines, and the time for this particular for this particular applications, it's on the y-axis. So as you can see, as you add more machines, as you'd expect, the time will go down. But after a while, the time is actually going to slowly increase. Why is that? Because for this particular application, as you start to use more machines, in this case more than whatever 40, the communication becomes a bottleneck. So you send more and more data over the network. So in this case, if you have a deadline, say you want to do your stuff in something like few hours, this is an orange line, then you can see that the optimal number, it will be 40 machines. Or 20, actually 20 in this case, sorry, right? So if you spend more money and you go to 100 or 120 machines, you won't get any benefits. You are just going to spend more money, okay? So this figure just shows these orange dots, just tells you how accurate in prediction is Eamest. The dark line is the real execution of the job. With orange, or the orange dots is a prediction given by Eamest. So in this case, the prediction is very good. You are just only between 10 and 50% off from the real execution time. Finally, here it's a more realistic application. There are a set of two operations in a genomics pipeline we built at Berkeley, Adam. And just look at the first 2 top group of bars. Here we have 2 configurations with orange, 45 R3X large instances, and green and blue is 64 M3 to X large instances. On the left-hand side, you see the time, how long it takes to run these operations. On the right-hand side, you see the price for each configuration. So if you look for marked up at the top, if you use 45 R3X large instances, you can do it 1.x times faster. And by the way, this will be 20% cheaper. So in this case, you can get over 2x better performance price ratio if you use the right configuration. So we are going to wrap up. So in summary, today's Apache Spark is a de facto standard for big data processing. It's growing faster than ever across almost every metric. And this year, we are very excited about release of the version 2.0, which again represents the biggest improvement since the original release. Today, AWS is the best cloud platform to run Apache Spark. Again, we developed Apache Spark very early on AWS. And like Rahul said, Apache Spark is a computation engine, right? It's not a storage engine. It can process the data from any storage you have. Anywhere it's stored in AWS, you have your data stored, you can use Apache Spark to process it. It can take advantage for different workloads of all these AWS instances you can choose from. And I just shown you this tool, Earnest, which can help you to select the optimal number and type of instances for your particular job. So with this, I think we have time for a few questions.